The 19th century belonged to steam, the force that drove the industrial world. Yet on the high seas, the age of steam was still an era of compromise defined by noise, vibration, and inherent inefficiency. Great naval powers relied on massive reciprocating piston engines, machines of cumbersome power that shook the hulls and wasted vast amounts of precious energy. Naval supremacy was defined by these limitations. And then, in a single audacious moment, everything changed. The year was 1897. The Royal Navy's elite were assembled at the Spithead Fleet Review, a magnificent display of maritime strength. They watched their iron-clad ships churning along, their speed constrained by the rhythmic shudder of their massive engines. Suddenly, a blur appeared on the horizon. A tiny, 100-foot experimental vessel tore through the review lines, moving at a speed the Admiralty had dismissed as impossible. 34 knots. The vessel was the Turbinia, and its performance that day was more than a spectacle. It was the abrupt introduction of a new strategic reality. The Turbinia had completely outpaced the fastest warships of the Royal Navy. Its secret lay in an invention born 13 years earlier: the modern steam turbine. The inventor, Sir Charles Parsons, had devised a radical machine that converted pressurized steam into continuous rotational power through staged spinning blades. This eliminated the wasteful stop-start cycles of the piston engine, delivering smooth, uninterrupted, and potent speed. The Admiralty witnessed not just speed, but a mechanical transformation. This technology would empower the British Navy across 2 world wars, enabling faster maneuvers and reliable performance under combat stress, though its adoption would come with significant strategic costs and complex engineering challenges. The era of the slow, shaking engine was over. Charles Algernon Parsons was born in 1854, the son of a pioneering astronomer who constructed the Leviathan of Parsonstown, the largest telescope in the world at the time. This environment instilled in young Charles a profound passion for precision engineering and the continuous elimination of error. Parsons carried that passion through his education at Trinity College, Dublin and Cambridge. His early career focused on electricity generation, and it was while observing dynamos powered by the inefficient, violent reciprocating engines of the day that he recognized the fundamental problem. Parsons was determined to harness the relentless pressure of steam into a continuous, perfectly efficient motion. His design was a marvel of mechanical simplicity and engineering complexity. High-pressure steam was expanded through a series of multi-stage blades, capturing the energy in a smooth, rotating action. Years later, reflecting on his design philosophy, in his 1911 Reday lecture, Parsons stated, "It seemed to me that moderate surface velocities and speeds of rotation were essential if the turbine motor was to receive general acceptance as a prime mover. I therefore decided to split up the fall in pressure of the steam into small fractional expansions over a large number of turbines in series, so that the velocity of the steam nowhere should be great. I was also anxious to avoid the well-known cutting action on metal of steam at high velocity." The turbine offered revolutionary benefits: a significant reduction in fuel consumption and an almost total elimination of the vibrations that plagued earlier marine power plants. Initial resistance was high, primarily because the turbine's optimal speed was far too high for ship propellers, risking the formation of vapor bubbles that reduced thrust and caused rapid erosion. Parsons overcame this by using 3 turbines on the Turbinia, driving 3 separate propeller shafts. By 1900, his designs offered speed increases of 15% to 20% and vastly extended operational ranges. These factors, extended range and reliability, were the strategic attributes that would directly enable the Royal Navy's global deployments. Despite the dazzling speed of the Turbinia, the Royal Navy's initial adoption was cautious. The technology was radical and expensive, requiring entirely new metallurgy and manufacturing precision. However, the international arms race made the speed advantage irresistible. In 1899, the Admiralty commissioned the first turbine-powered destroyers, HMS Viper and HMS Cobra, capable of achieving an astonishing 37 knots. The numbers confirmed the future of naval propulsion. The Turbine's ascent culminated in 1906 with the launch of HMS Dreadnought. This battleship was the physical embodiment of a technological leap, the first all-big-gun warship, and crucially, powered entirely by Parsons' direct-drive steam turbines. The Dreadnought achieved 21 knots, a speed its contemporaries could not match, instantly rendering every other battleship obsolete. This single vessel intensified the Anglo-German naval arms race. The German response, the Nassau-class battleships launched in 1908, utilized turbine propulsion but were slower at 20 knots, forcing Berlin to escalate naval budgets and competition dramatically to regain parity. The economic factor was paramount. Admiralty reports noted the high initial construction costs of turbine plants, but justified them based on projected fuel savings, estimated at 20% less coal or oil than equivalent reciprocating engines. Furthermore, Parsons, having regained control of his critical patents in 1894 after disputes, began global licensing. This spread the technology rapidly to rivals, including US firms like Curtiss, diluting Britain's exclusivity, but establishing the turbine as the universally accepted prime mover. The new engine was not just for warships. Early merchant adoption, such as the transatlantic liner RMS Victorian, showcased the smooth efficiency that would prove vital for maintaining wartime convoy logistics. By the time the Great War erupted in 1914, the Parsons turbine powered most major vessels in the Royal Navy, providing the speed and, critically, the reliability needed for massive fleet actions. By 1914, the Parsons turbine was the naval standard. Its strategic performance was measured not just in top speed, but in operational reliability and endurance. The turbine's design eliminated the immense racking vibration of piston engines, minimizing wear and tear. This meant less time in dock for repairs and greater time on station, a crucial factor for the Grand Fleet's mission to enforce the North Sea blockade. Winston Churchill, then First Lord of the Admiralty, praised the technology, noting that the turbines enabled the Grand Fleet's unceasing vigil, highlighting its indispensable role in the long-term blockade endurance. The ultimate test came in 1916 at the Battle of Jutland, the only full-scale clash of dreadnoughts. This was a maelstrom of steel and smoke. Shells the size of small cars rained down, turning the North Sea into a boiling, metallic cauldron. In this chaos, speed became the key to tactical survival. The British battle line, powered entirely by Parsons turbines, did not shudder or hesitate. They could maintain a blistering 25 to 28 knots, not just in a straight line, but through violent, sustained manoeuvring under continuous fire. Deep below the decks, however, there was no glory, only punishing work. In the vast, throbbing engine rooms, the turbine crews, known simply as stokers and engineers, fought their own battle. Surrounded by superheated steam and the deafening high-pitched whine of the rotating machinery, they pushed the boilers past their red line limits. The temperature could exceed 120 degrees Fahrenheit. Their job was not just to maintain the speed, but to ensure the delicate turbine blades and precision reduction gearing did not seize under the immense stress of continuous maximum output. The reliability of Parsons' design was a testament to their endurance and technical precision under unimaginable combat pressure. This consistent, reliable power delivery allowed Admiral Sir John Jellicoe to execute a decisive, high-speed deployment that led to the critical manoeuvre known as crossing the T, positioning the British column perpendicularly to the German column for a broadside advantage. This fleet-wide manoeuvre, achieved at speed, would have been impossible with the older, unreliable reciprocating machinery. The sheer readiness of the fleet, enabled by Parsons' work, was noted by Jellicoe himself. The Grand Fleet could turn the scale of the war in an afternoon. Naval reports confirm that the Turbine's consistent performance reduced repair downtime by an average of 30% compared to older ships, enabling the fleet to remain at sea for over 2,000 days while enforcing the blockade. This relentless efficiency created significant strategic frustration for the Germans. Admiral Reinhard Scheer, commander of the German High Seas Fleet, later reflected in his memoir that the high speed maintained by the British ships was crucial in allowing them to dictate the terms of engagement, evade entrapment, and often compel a German retreat. Beyond the great fleet actions, turbine speed proved tactically indispensable in specialized operations. For instance, in the daring Zeebrugge raid in 1918, high-speed turbine-powered destroyers were critical for laying smoke screens and covering the rapid approach and withdrawal of the block ships during the precise, time-sensitive assault on the German U-boat base. However, the initial direct-drive turbines were not without their flaws. The very nature of their high-speed design meant that during extended patrols at low cruising speeds they were wildly inefficient, consuming excessive fuel. This early fuel inefficiency often resulted in fuel shortages for squadrons on long, distant patrols, forcing early returns to port and foreshadowing the necessity of the geared turbine refinements that would dominate the interwar period. The Germans retreated at Jutland and never again seriously challenged the supremacy of the British Grand Fleet. The experience of World War I proved the turbine's speed but highlighted a technical limitation: efficiency at low speeds. The solution, which defined the interwar period, was the geared turbine. Parsons' engineers perfected the double reduction gearing system, a precision-cut gearbox that mechanically separated the high-speed turbine from the slow-turning propeller. The turbine could now spin at its most efficient rate, up to 3,000 revolutions per minute, while the propeller spun at its optimal speed, around 300 revolutions per minute. The initial introduction of this system in destroyers like HMS Badger was followed by rapid refinement throughout the 1920s. This technical achievement had profound strategic and economic implications. Fuel consumption plummeted, granting naval vessels vastly extended operational ranges. This was critical during the post-World War I era, where the Washington Naval Treaty imposed severe restrictions on warship building. With tonnage limited, naval architects were forced to focus on efficiency. Parsons' company, which had supplied over 10 million shaft horsepower during World War I, adapted by developing high-pressure, high-temperature steam systems to further squeeze efficiency. The result was ships like the County-class cruisers, which achieved ranges exceeding 8,000 nautical miles, a vast improvement in global reach. An assessment by the Institution of Mechanical Engineers noted that gearing was responsible for extending endurance by 20 to 30% across the board. The downside, however, was technical conservatism. Naval engineer Louis Le Bailly later described the resulting Royal Navy turbine plants as reliable but conservative compared to higher pressure, lighter American designs, noting this technical conservatism was partly a result of the interwar slump's impact on innovation and the scarcity of highly skilled labor available to risk new, complex designs. The Second World War tested the turbine's endurance across global theaters, from the frigid Arctic to the tropical Pacific. The refinement of the geared turbine was now the mechanical foundation for Britain's survival, crucial for maintaining the supply lines across the Atlantic. The Tribal-class destroyers, the spearhead of the Royal Navy's anti-submarine efforts, were powered by geared turbines generating up to 44,000 shaft horsepower. This massive power translated to a top speed of 36 knots. This speed on demand, coupled with the improved endurance, was vital for anti-submarine warfare, allowing destroyers to rapidly run down surfaced U-boats. The operational tempo was immense, Destroyers in crucial convoy groups like Convoy HX-300, the largest of the war, logged over 100,000 miles per ship. But the ultimate drama unfolded in May 1941. Following the swift, brutal sinking of HMS Hood, the pursuit of the German battleship Bismarck became an all-consuming mission for the Admiralty. The challenge was not just to find the ship, but to hold contact and close the distance across 900 miles of violent North Atlantic seas. This was the Turbine's finest hour. The pursuit demanded unrelenting speed and endurance. Flagship HMS King George V and her escorts utilized their geared turbine plants to push maximum output, generating approximately 110,000 shaft horsepower, hour after hour, day after day. In the deafening engine rooms, the turbine's continuous rotation was the heartbeat of the chase. Engineers worked at the limits of the machinery, feeding high-pressure steam into the blades, knowing that a single mechanical failure would mean losing the prize and sacrificing strategic victory. This sustained velocity was impossible for any engine of the previous era. Reciprocating pistons would have seized or broken down under such continuous strain. The turbine, however, absorbed the punishment. After days of high-speed steaming in brutal weather, the British fleet finally closed the gap. The victory was secured not just by firepower but by the fundamental mechanical fact that the British engines held up under this unrelenting stress while the Bismarck's own propulsion system had been damaged and compromised. The speed gifted by Parsons delivered the killing blow. Beyond the Atlantic, the turbine's versatility was crucial in other theatres. In the Mediterranean, speed enabled surprise attacks. The turbine-driven ships of Force H, including the carrier HMS Ark Royal, used their pace to execute the 1940 Taranto raid, proving the value of fast carrier-based strikes. In the Pacific, turbine-powered carriers like HMS Illustrious were able to support the challenging Okinawa operations, enduring long transits and high-intensity flying operations. Overall, the consistent reliability provided by the turbine design ensured that the Royal Navy maintained an operational readiness rate of over 80% for its 900-plus warships, a statistic vital to the war effort. This technical superiority was consistently proven across diverse tactical situations. In World War I, the speed and low vibration provided by the turbine were vital for the high-speed maneuvers at Jutland, but also in other campaigns. During the challenging Dardanelles campaign in 1915, while the overall operation failed, the ability of turbine-powered destroyers to make quick maneuvers and sustained high-speed runs during evacuations was critical for minimizing casualties and saving lives. The turbine's performance continued to be tested in the extremes of World War II. In the Battle of the Barents Sea 1942, turbine-powered destroyers like HMS Onslow repelled superior German raiders. The destroyers used their high-speed capability in the freezing Arctic conditions to lay smoke screens and evade fire, demonstrating that the engine's power was a tactical shield as much as a weapon. However, the pursuit of efficiency and speed came with its own risks. The complexity of the geared turbine plants, while robust, meant that maintenance at sea was difficult, and occasional failures did occur. For instance, the high-speed maneuvers and intense use led to occasional mechanical issues, such as those that plagued the turbine reduction gearing on HMS Prince of Wales in 1941, illustrating the difficult balance between performance and absolute reliability required for complex war machinery. Despite these isolated drawbacks, the turbine's overall operational resilience was the key differentiator. It allowed the British to maintain tactical control, forcing the enemy to react to the superior speed and maneuverability of their fleet. Sir Charles Parsons died in 1931, well before the true existential test of his life's work. Yet the story of his invention is incomplete without acknowledging the men who tended it, the engineers, stokers, and engine room staff. The turbine was quieter, smoother, and vastly more powerful than the piston engine, but operating it demanded a new level of precision. In the heat and deafening roar of the turbine chamber, engineers monitored the precise pressure, temperature, and flow of superheated steam, often near 700 degrees Fahrenheit, in confined spaces. Their commitment to the steady, smooth functioning of the turbine reflected Parsons' own passion for order and precision. The technical demands of the war effort placed incredible strain on these crews. Veteran accounts detail the constant fight against feed pump failures and the need to manage high-pressure steam systems under combat stress. They had to maintain precision machinery under fire, ensuring the complex gearing remained lubricated and balanced, making them the ultimate human guarantors of the fleet's propulsive advantage. The turbine's strategic value was often illustrated in unique ways. In March 1915, HMS Dreadnought, powered by Parsons' direct-drive turbines, detected a German submarine, the U-29, surfaced in front of it. The great battleship, designed to fight other battleships, was able to execute a sudden, aggressive turn that allowed it to ram and sink the submarine, the only time a battleship achieved this feat in history. The strategic legacy of Parsons' invention is clear. It solved the problems of attrition and range that had historically limited naval dominance. The engine was a force multiplier, ensuring that the Royal Navy could deploy globally and sustain its operations with efficiency and confidence. Furthermore, Parsons' influence extended beyond the war. His continuous flow principles laid the essential groundwork for nuclear propulsion in submarines. On the social front, his wife, Lady Catherine Parsons, continued his legacy by helping to found the Women's Engineering Society in 1919, ensuring the expertise honed during the war was utilized in peacetime innovation. Although C.A. Parsons and Company eventually became part of Siemens, the core design remains the fundamental basis of steam turbine power worldwide. The steam turbine stands as one of the most significant mechanical inventions of the industrial age. It provided the most efficient means yet devised to convert thermal energy into large-scale, continuous motion. The story of the Parsons turbine is the story of how an obsession with efficiency translated into a profound naval advantage that helped secure Britain's place as a supreme naval power in the 20th century. The legacy of Sir Charles Parsons extends far beyond the oceans. His fundamental work on compressing and expanding fluids through staged blades directly inspired pioneers like Frank Whittle in the 1930s, who developed the jet engine based on the continuous flow gas turbine concept. Today, the direct legacy of the turbine is twofold: in energy and naval power. More than 80% of global electricity generation relies on steam and gas turbines built upon his original blueprint. Even modern surface combatants, such as the US Navy's Arleigh Burke-class destroyers and the Royal Navy's own HMS Queen Elizabeth-class carriers, utilize sophisticated gas turbines for their primary propulsion, proving the enduring strategic value of the rotational engine. From the Grand Fleet to the modern power grid, Parsons' obsession with converting kinetic energy into useful work transformed society. His life's work perfectly embodied his philosophy. The object of all invention should be the elimination of waste. This ethos resonates today not only in mechanical efficiency, but in the global drive for sustainability, where maximizing energy output from available resources is paramount. As one engineer recently observed, Parsons gave us the tool to manage power on a massive scale. His turbine is the grandfather of the modern world's energy backbone. The conflict for global supremacy was won, in part, by the turbine's reliable, high-speed horsepower, which was essential alongside other factors like radar and code breaking. It was the mechanical underpinning of command of the seas, a force that ensured the British Navy could fight when they liked, where they liked, and how they liked. Parsons' invention was the unsung hero of the seas, ensuring that the unyielding efficiency and speed of the Royal Navy were available when needed most. the fate of the empire was ultimately secured by the smooth, unwavering, and factually precise revolutions of a wheel of steam.